Welcome again to the lecture series of signals and systems. In the previous lecture, we have seen some important properties of the discrete time Fourier series, Fourier transform, and we are left with one more important property which is called Parseval's theorem to determine the energy of discrete time signals. So we are left with only one more property of DTFT, and after discussion of this property we will move to the Laplace transform. So the Parseval's theorem says that Parseval's theorem, or we can call it Parseval's property, that energy of a signal in the time domain can be determined by using the relation that is from minus infinite to plus infinite mod of xn square. And if the Fourier transform, discrete time Fourier transformation of this signal, xn is x of omega. Suppose discrete time Fourier transform of this signal, xn is capital X of omega, then this summation or this energy can be written as 1 upon 2 pi integration from minus pi to pi mod of x omega square dv. This is what the Parseval's property states, that the energy of the signal in the frequency domain can be determined by using this integration, which is 1 upon 2 pi integration for one time period mod of x of omega square d omega. So the proof of this property: if the Fourier transform, suppose Fourier transform of xn is x of omega, then energy of the signal E can be written as sigma n is from minus infinite to plus infinite mod of xn square, or I can write it as sigma n is from minus infinite to plus infinite xn into x conjugate n. Mod of xn square can be written in this way. It can be written as xn into x of xn of conjugate of xn, and this further can be written as sigma n is from minus infinite to plus infinite xn into x of n conjugate. And we know that the inverse DTFT can be determined by using, means we can obtain the signal xn from x of omega by using this relation. Xn is equal to 1 upon 2 pi minus pi to pi x of omega into e power j omega n d omega. By using this relation, we can find the signal xn from x of omega. So in place of xn, I can put 1 upon 2 pi, limit from minus pi to pi x of omega e power j omega and d omega. I can replace xn in this relation by this value of xn. So this will become E is equal to sigma n is from minus infinite to plus infinite. I will write this xn as it is, and in place of this xn I will write 1 upon 2 pi integration for one time period x of omega e power j omega and d omega conjugate. Now further this can be written as, further this relation can be simplified as this is equal to sigma n is from minus infinite to plus infinite, and this is x of n 1 upon 2 pi integration from minus pi to pi, and this will become x conjugate omega into e power minus j omega n. After conjugation, this will become e power minus j omega n d omega. Or I can simply change the order of this integration and summation as we can change the order of summation and differentiation, and after changing, this will become as changing the order of summation and integration. After changing the order of summation and integration, this relation will become E is equal to sigma. This will become sigma x of omega, or we can write in this way. This will become integration from minus pi to pi. Here 1.2 pi is here. X of omega integration. This is not integration. This is different summation of xn, and I will combine these two terms. Xn with e power minus j omega n with this summation, and this will be separated 1 upon 2 pi x star of omega d omega. This will be separated. So I will write here it is omega d omega into sigma n is from minus infinite to plus infinite xn e power, this is e power minus j omega n. And if we observe clearly, this function xn e power minus j omega n is the discrete time Fourier transform of the given signal xn, which is equal to, this is equal to x of omega, means discrete time Fourier transform of the given sequence x of n. It means that this energy further can be written as 1 upon 2 pi integration from minus pi to pi x of omega into x conjugate of omega d omega. And we know this property that if we multiply two functions as x star t into xt, then this will become mod of x of t whole square. So I can write this as E is equal to 1 upon 2 pi minus pi to pi mod of x of omega whole square d omega. This is how we can find the energy of a given signal if its discrete time Fourier transform signal is known to us, and this property is called Parseval's property or Parseval's theorem. So if the discrete time Fourier transform of the signal xt is x of omega, then we can find the energy of this signal either by using this relation 1 upon 2 pi limit from minus pi to pi mod of x of omega square d omega, or we can simply find the energy of the signal by using the relation n is from minus infinite to infinite mod of xn square. We can use any one of them to find the energy of a given sequence x of n. With this, the properties of discrete time Fourier signal is completed, and we will consider some one or two examples and then move to the next important tool, which is Laplace transform. Suppose the given signal xn is equal to 1 by 3 power mod of n minus 2 u of n minus 2, and we have to get the discrete time Fourier transform of this signal xn. The signal given here is 1 by 3 power mod of n minus 3 into u of n minus 3, and we have to find the discrete time Fourier transform of this given signal. We know the formula to calculate the discrete time Fourier transform. The Fourier transform of signal of the given sequence xn will be equal to sigma n is from minus infinite to plus infinite xn into e power minus j omega n. By using this relation, we can find out the discrete time Fourier transform of the given sequence x of n. Now, instead of getting the discrete time Fourier transform of this sequence 1 by 3 power mod of n minus 2 into u of n minus 2, we can find the Fourier transform of of 1 by 3 power n u n. And suppose the Fourier transform of 1 by 3 power n u n is x of omega, then Fourier transform of 1 by 3 power n minus 2 u of n minus 2 will be equal to e power minus j to omega x of omega. This is simply time shifting property. Means if we are shifting the signal in the time domain by 2 units to the right, then signal in the frequency domain will be multiplied by e power minus j to omega. Now that means we have to find the Fourier transform of this signal only, and in the Fourier transform of this signal we will multiply with this quantity e power minus 2j omega. So the task is to find the Fourier transform of e power minus j 1 by 3 power n. We have to get the Fourier transform of this signal. Then suppose xn is equal to 1 by 3 power n u of n is equal to xn. Now to get the Fourier transform of this xn, we will write it as, in place of xn I will put here 1 by 3 power n, and because un is also here, so this limit will become from 0 to infinite. Because of this union, because un exists only for the positive values of the time, so I will put here value of time from 0 to infinite. This will become e power 1 by 3 power n e power minus j omega n. Or also we can write it as, this will become 3 power, this will become 3 e power j omega n power minus n, where n is from 0 to infinite. I can write it in this way, or this can be written as sigma n is from 0 to infinite 1 by 3 e power j omega n e power 3, this n will not here, e power 3 j omega power n, because when this will go in the numerator, this will become 3 power n minus 1, and this will become e power minus j omega, and then this will become 3 power minus n e power minus j omega n. So this relation can be replaced by this quantity, and this will become, because limit is from 0 to n, 0 to infinite, this will become 1 by, the first term will become, when n is equal to 0, when I will put n equal to 0 in this relation, this will become 1. So I will write it as 1 plus 1 by 3 into e power j omega plus 1 by 3 into e power j omega square plus 1 by 3 into e power j omega cube plus so on till the infinite. So this is a GP, and having the first term a is equal to 1, r is equal to 1 by, r is equal to 1 by 3 e power j omega, and number of terms are infinite. So this summation will be equal to, this summation of this series will be equal to a upon 1 minus r, a upon 1 minus r, means this will be equal to 1 upon 1 minus 1 by 3 e power j omega, or this can be written as 1, this will become e power 3 e power j omega upon 3 e power j omega minus 1, or if we divide with 3 into e power j omega in the numerator and denominator, this will become divide with 3 into e power j omega in numerator and denominator, then this relation will become, this is the Fourier transform of 1 by 3 power n u of n will be equal to, divide with 3 into e power j omega, this will become 1 upon 1 minus e power 1 minus 1 by 3 e power j omega, or this can be written as 1 upon 1 minus 1 by 3 into e power minus j omega. This is the Fourier transform of this given sequence, and we want the Fourier transform of 1 by 3 e power mod of n minus 2 u of n minus 2. So because there is a shifting of 2, so I will multiply simply the signal with e power minus j 2 omega upon 1 minus 1 by 3 into e power minus j omega. So this is the way how we can apply the time shifting property of the discrete time Fourier transform to get the Fourier transform of the given signal. Now consider another example in which we have to find the, we have to apply the property of shifting, time shifting property. The given signal is delta n minus 2 minus delta n plus 2. The given signal xn is equal to delta n minus 2 minus delta n plus 2. This is another case of time shifting, because Fourier transform of delta n is known, and we have to get the Fourier transform of delta n minus 2. Similarly, we can find the Fourier transform of delta n plus 2. So we know the Fourier transform of delta n is, Fourier transform of delta n is equal to 1, then Fourier transform of delta of n minus 2. Again, here it is time shifting in the signal by 2 unit. So I will multiply the right side of the frequency domain of this signal by e power minus j2 omega. Similarly, if the Fourier transform of delta n is 1, then to get the Fourier transform of delta n plus 2, the signal in the frequency domain will be multiplied by e power plus j2 omega. And if we have to get the Fourier transform of delta n minus 2 minus delta n plus 2, this will be equal to Fourier transform of delta n minus 2 minus Fourier transform of delta n plus 2. This will be equal to Fourier transform of delta n minus 2 will be equal to e power minus j2 omega minus e power plus j2 omega. I can write this as minus of e power j2 omega minus e power minus j2 omega, and if we multiply this by 2j and divide by 2j, this is the formula of sinusoidal signal in the form of exponential. Then this will become minus of 2j sine 2 omega. This is another example of how we can apply the time shifting property in the discrete time Fourier transform to get the Fourier transform of a given signal. So these are some more examples related to discrete time Fourier transform. Now consider a case. Suppose we have to get the Fourier transform of the signal. Suppose we have to get the Fourier transform of the signal. Suppose the given signal in the continuous time domain is e power 3t ut, and we have to get the Fourier transform of this signal. We know the relation to get the Fourier transform of a given signal, which is given as Fourier transform of x of t will be equal to sigma t is from minus infinite to plus infinite x of t into e power minus j omega t dt. This is how we can get the Fourier transform of a given signal. Here the given signal is e power 3t ut, so I can write it as t is from minus infinite to plus infinite e power 3t into e power minus j omega t ut dt. Or further, because ut is here, I can remove ut from here by putting the limit simply from 0 to infinite e power 3 minus j omega into t dt. Or we can write it as integration from 0 to infinite e power minus j omega minus 3 into t dt. This can be further written as integration of e power minus j omega minus 3 into t upon minus j omega minus 3, where limit is from 0 to infinite. When I will put the value of t here equal to, this is from 0 to infinite, when I will put t is equal to infinite here, this will become in e power minus infinite, and e power minus infinite means this will become 0 minus, when I will put the lower limit, 1 minus is already here, this will become plus and lower limit is 0. So when I will put t equal to 0 here, this will become 1 upon j omega minus 3. So this should be the Fourier transform of the given signal e power 3t ut. This should be the Fourier transform of this given signal e power 3t ut. But anyway, we cannot find out the Fourier transform of this signal by using this relation of the Fourier transform directly, because if we see clearly, e power 3 tut is an unbounded signal, and if the signal is unbounded, this will not follow the Dirichlet condition, which states that to find the Fourier transform of a given signal xt, to find the Fourier transform of the given signal xt, this signal xt should be integrable in the range from minus infinite to plus infinite. Means the signal xt should give a finite value when it is integrated from in the interval from minus infinite to plus infinite. Now check this criteria. If this signal is satisfying the criteria, Dirichlet condition or not. To check, we have to check whether the given signal is absolutely integrable or not, and the given signal is e power 3 dut. So for the existence of the Fourier transform, this signal xt mod of xt should be integrable, or we can say that should give a finite value when it is integrated in the interval from minus infinite to plus infinite, which is called Dirichlet condition for the convergence of the Fourier transform. So in place of xt, I will put here e power 3t ut dt, or we can write it as sigma, because ut is here again. I will remove this by simply putting the limit from 0 to infinite e power 3t dt, and we know the integration of e power 3t is e power 3t by 3, limit is from 0 to infinite, and this will become e power infinite minus e power 0 by 3, and this will go to the infinite, because the given signal e power 3t ut is not absolutely integrable. It will not follow the Dirichlet condition for the existence of the Fourier transform. So we cannot apply the formula of the Fourier transform to get the Fourier transform of this signal directly. That's why if we calculate the given signal, if we determine the Fourier transform of the given signal by simply using the Fourier transform pair, this will give a wrong result. So what we will do to get the Fourier transform of this signal, how we can convert such type of signals from their time domain to frequency domain. So suppose there is another signal. Suppose it is x dash t is equal to e power minus sigma. Suppose there is another signal x dash t is equal to e power minus sigma t ut, or we will not put ut, it doesn't matter because one ut is already there. If we will multiply these two signals, xt into x dash t, x of t into x dash of t, then this will be equal to e power 3t into e power minus sigma t and ut. Now this will become equal to e power 3 minus sigma into t u of t. Now check whether this signal is absolutely integrable or not. So I will put here t is from minus infinite to plus infinite e power 3 minus sigma into t dt, and this will become e power 3 minus sigma into t dt, because I will not putting ut here means we can remove ut from this relation simply by putting the limit from 0 to infinite, because existence of ut is only for the positive values of time. So I will put the limit here from 0 to infinite. Now this will become e power 3 minus sigma into t divided by 3 minus sigma, where limit is from 0 to infinite. Putting the upper limits, this will become e power 3 minus sigma 3 minus sigma into infinite minus e power 3 minus sigma into 0 divided by 3 minus sigma. So now this relation also will give value equal to infinite, but for a particular, for some particular values of sigma, this integration can converge. How? If the given value of, suppose this value 3 minus sigma is less than 0. Suppose 3 minus sigma is less than 0. Means this value is negative. If this value is negative, then this will become e power minus infinite, and e power minus infinite will become 0. Then this integration will give e power 0 upon 3 minus sigma. This will converge for a certain condition that this 3 minus sigma should be less than or less than 0, means this sigma should be greater than 3. If this condition exists, if this condition will exist, we can find out the Fourier transform of the given signal also. It means that the signals for which the Fourier transform is not existing, because the given signal is not absolutely integrable. If we multiply this signal with another signal e power minus sigma t, then for the certain condition on this signal may also converge, or we can say that we can find out the Fourier transform of this signal also by multiplying with another quantity e power minus sigma. So look what will happen if we are going to multiply the signal with e power minus sigma t. This will become, so instead of xt, instead of getting the Fourier transform of x of t, I will determine the Fourier transform of x of t into e power minus sigma t. X of t into e power minus sigma t, and by relation we know that the Fourier transform of the signal will become t is from minus infinite to plus infinite xt e power minus sigma t into e power minus j omega t dt. If I will multiply the given signal xt with a quantity e power minus sigma t, then I can write the Fourier transform of the xt in this way, and this can be further simplified as this is equal to minus infinite to plus infinite x of t e power minus sigma plus j omega t another variable defined by the Laplace. This sigma plus j omega is equal to s. Another important variable, s is equal to sigma plus j omega, because when we are calculating, we are determining the roots of a polynomial. Sometimes we get complex roots, sometimes we get imaginary roots, sometimes we get only real roots. So for that purpose, Laplace has considered a variable which have all the parts. It is complex, it may become real, it may become imaginary. So S is a complex number. So in place of this sigma plus j omega, this can be written as t is from minus infinite to plus infinite xt e power minus st dt, and this is the formula of Laplace transform of x of t. So by using this relation, we can find out the Laplace transform of the given signal. So Laplace transform is nothing but it is the Fourier transform of the signal xt multiplied with another quantity e power minus sigma. Or we can say that Fourier transform is a special case of the Laplace transform for sigma is equal to 0. If I will put sigma equal to 0 in this relation, if I will put sigma equal to 0 in this relation, then S will become equal to plus j omega, and this relation will become t is from minus infinite to plus infinite x of t e power minus in place of s, now I will put j omega minus j omega t dt. This is the formula to get the Fourier transform of the given signal xt. It means that the Fourier transform is a specific case of the Laplace transform. It's a special condition of the Laplace transform in which we consider this real part of the S sigma is equal to 0. If we consider sigma equal to 0 in the Laplace transform, this will become Fourier transform of the given signal xt. Or we can say that if I will put S is equal to j omega in the Laplace transform, the transform will become Fourier transform. Or we can say that the Laplace transform is the Fourier transform of the signal xt multiplied with e power minus sigma t. So here we can say that this is a more generalized form. Laplace transform is the more generalized form than the Fourier transform, and Fourier transform is a special case of the Laplace transform. So by using this relation, we can find out the transform. We can transform the such signals also which does not those signals which are not absolutely integrable in the range from minus infinite to plus infinite. So the signals for which we cannot find the Fourier transform, we can find the Laplace transform for those signals also, but with a certain condition on sigma, as we seen in the previous case that sigma should be greater than 0. So if the signal is not absolutely integrable, we cannot find the Fourier transform of that signal, but we can find the Laplace transform of that signal with certain conditions, and this certain condition on sigma is called region of convergence. This limitation on the sigma is called region of convergence. This region of convergence is not required for the Fourier transform, because in the Fourier transform we already considered that this signal xt is absolutely integrable, and if the xt is not absolutely integrable, we cannot determine the Fourier transform of such signals. But we can determine the Fourier transform of we can determine the Laplace transform of such signals which are not absolutely integrable with certain conditions of sigma, and this condition is known as region of convergence for the given signal xt to find the Laplace transform of this signal. So This is the way I can determine the Laplace transform of a given signal, but we have to consider this another new term also, that there would be a certain condition on the sigma so that we can find out the Laplace transform of the given signal. So we have seen to get the Fourier transform, the signal xt should be absolutely integrable, and in place of xt here, it is xt into e power minus sigma t. So for the convergence of Laplace transform, the important condition is this signal xt x of t into e power minus sigma t dt should be absolutely integrable. In place of xt here, it is xt into e power minus sigma t dt. So, for the existence of Laplace transform, this condition should be followed, that modulus of xt into e power minus sigma t dt should be absolutely integrable, means it should give a finite value when it is integrated from minus infinite to plus infinite, and this will happen only for some certain values of sigma, only some specific values of sigma, and these specific values of sigma for which this relation exists means, sorry, these specific values of sigma for which this integration, this signal xt becomes absolutely integrable. These values of sigma are known as region of convergence for the existence of the Laplace transform. Means the Laplace transform of this signal will exist only for sigma greater than 3. So those values of sigma for which this signal becomes absolutely integrable, those values are called region of convergence of the Laplace transform. So this is the difference in the Fourier transform and Laplace transform, that the Laplace transform is defined only for the certain range of the sigma, which is called ROC, whereas Fourier transform can be determined if the given signal xt is absolutely integrable, and we can find the Laplace transform of the signal even if the signal is not absolutely integrable. So these are the differences. We will discuss some more important points about the Laplace transform in the next lecture. So this is all for today. Thank you.